in addition to anthropic principal characteristics of the Earth, in other words, those evidences that would suggest that the Earth looks like it was created for humans, there are also AP characteristics, anthropic principal characteristics for the solar system. Things in the solar system make it look like the solar system was made with humans in mind. For example, when we look at our moon, there are larger moons in the solar system than the moon of the Earth. But if you look at the comparison of the size of the moon with the Earth that it orbits about, it is a very large moon compared to the Earth. It is a much larger percentage, the moon is a much larger percentage of the mass of the Earth than any moon around any other object is to the object around which it's moving. So there are moons of Jupiter that are bigger than the moons of the Earth, than the moon of the Earth. There are moons of Saturn that are bigger than the moon of the Earth. But the moons of Saturn compared to Saturn, or the moons of Jupiter compared to Jupiter, are really minuscule, are really very small. The moon around the Earth, our moon, is so huge that it has a very large impact upon the Earth. It in fact changes the orbital motion of the Earth, slowing the orbital motion of the Earth. It keeps the Earth from wobbling as much as other planets naturally wobble. It also creates tides on the surface of the Earth, tides that are in fact very important for some organisms of on the planet. That wobble that the moon prevents on our Earth, in fact, stabilizes the climate on the Earth in a very unique way. Unlike any other planet in the solar system, we have a much more uniform climate, one much more conducive to life on the Earth. Also, if we look at the distance the Earth is away from the Sun, the Earth is sitting in what's called the Goldilocks zone. This is a zone around the Sun where if you are a little bit too close or inside that Goldilocks zone, closer to the Sun in the Goldilocks zone, it's too warm. You're too close to the Sun and the Sun heats you up too much. If you're too far from the Sun, beyond the Goldilocks zone, you're too cold. It's only in a narrow zone around the Sun that you are in the right distance away from the Sun to be warmed enough from the Sun that you're not too hot, and yet not too far away from the Sun to be too cold. To be just the right temperature, the Earth should be, and is, right in the middle of what we call the Goldilocks zone. Of course, you know what Goldilocks is, that fairy tale individual who went into the bear's house and tried the hot soup. It was too hot. And tried the cold soup, and it was too cold, and then took the soup that was right in between, the perfect zone soup. And the Earth is sitting in a place where it's not too hot, not too cold. It's in the Goldilocks zone around the Sun. That's a very nice thing, because in fact, if it wasn't, we wouldn't be able to have life on the planet. If it was too close to the Sun, it would be too hot. There would be no water on the surface. Things would not be able to survive because it's too hot. If it's too far away, it'd be covered with ice, and organisms couldn't live either. We also have a very unusual sun or star in the midst of our solar system. If you look up into the sky at the small lights up there, most of them are stars. And for a long time we said that the Sun is one of those stars, and it's just another one of those stars. But if you compare one star with another, you find that they're all unique. They're different from every other star. The Sun is different from every star in the sky. Very possibly there are no two stars that are exactly the same. They each have a different chemical composition. They each have consequently a different color, a different temperature, a different brightness, different behavior. Most of the stars in the universe are, how would you say it? They don't behave very well. They spew out too much heat at certain times and then pull back. They pulsate between hot and cold, or they spew out all sorts of nasty radiation. if you're around those kind of stars as a planet, it's not good to live. You've got too much radiation that's in fact destroying you or heating you up and cooling you off and changing all the time. Our sun is an unusual star. It is very stable. It doesn't change its temperature and light very much. It's a very calm star. In fact, it is so calm and so well behaved as a star that some people are inclined to say, you know, technically I would say the sun is not really a star. It's so much different from other stars. It's so calm, it's so uniform from other stars that it's almost as if it is specially designed to be the kind of sun that would produce a stable situation for the Earth itself. The sun is also a particular color. You look up there at, let's say, Orion, the beautiful constellation Orion, and one of the shoulder stars of Orion is a bright orange star, Betelgeuse. It's an enormous star of an orange, red-orange color. Other stars are blue, other stars are white, other stars are actually green. This color of the sun is a bit on the yellow side. It happens to be a perfect color for photosynthesis. If the sun's color changed too much, it would be outside the range of color that could be picked up by plants and made into food, and the energy of the sun be captured in photosynthesis. Of all of the different colors that our sun could be, the sun seems to be the perfect kind of color for picking up its energy and transferring it into food. If we move outward from our solar system to something a bit bigger, to the galaxy, our solar system contains the sun and the planets, including the Earth. Our solar system is sitting in a group of stars known as the Milky Way galaxy, which is thought to have something on the order of 100 billion stars. And the characteristics of our galaxy turn out to be just what they need to be for life to be possible on the Earth itself. If you look at our galaxy, and of course we're in it, and it's hard, you can't look at our galaxy from the outside, but as near as we can tell, our galaxy looks a lot like the Andromeda galaxy, which you can see in the constellation. It's the only galaxy that you can see with the naked eye. If you look at it under a telescope, you see that it's a spiral arrangement of stars with a big central disk with lots and lots of stars very close together, and then stars farther apart in this spiral portion of the galaxy. It is thought that our Milky Way galaxy looks very much like that. We are not in the middle or near the middle of the Milky Way galaxy. We're about 2/3 of the way out from the center of the galaxy to the edge of the galaxy, in a place where actually stars are not very close together. They're not very abundant. If we were sitting in the middle of the galaxy, we would be in a position where there would be so many stars around us, so close together, we wouldn't be able to actually even see outside of the galaxy. We could only see this, our whole sky would be covered with stars that we couldn't see outside of it. It would be a bright sky. We're sitting in a situation 2/3 of the way out where most of the time when we look up, we're looking out away from the galaxy. We're looking through a very thin layer of stars out away from the galaxy in either direction. Or if we look towards the center of the galaxy, we see this thing we call the Milky Way galaxy through the Milky Way, through the sky. That's where we're looking directly at the center of our galaxy. But every place else, we are free to look beyond our galaxy to other galaxies, which we otherwise wouldn't be able to do if we were sitting in any other position in the galaxy. Being outside the center has some really great advantages. Even though a vast percentage of stars are in the center, our chances of being in the center would be pretty high if it was a random choice of a star in the galaxy, because vast percentage of them are sitting in the center. If we were, though, we would be so close to other stars, there would be some consequences which would be very bad for life. For example, there are stars that seem to be blowing up on a very regular basis. Since there would be so many stars in the center of the galaxy, we would be much too close to too many stars which are blowing up at any given point in time, and we would be in danger of being snuffed out by the explosion of these stars. There's another issue that if we are too close to another star, the Earth might get pulled out of its orbit by another star, and if it gets pulled out of the Goldilocks zone of around the sun, things would get too cold and we would be exterminated in that fashion. If we were in the middle of the galaxy, there would be too much competition between stars. We would not be finding ourselves in a nice, stable Goldilocks zone around a star such as we are now. So our position, being 2/3 of the way out of the galaxy from the center, is just perfect for allowing our star, our sun, to supply the needs of the Earth without the Earth being in danger of being destroyed. We can pull out a little bit further, or maybe a lot further, from the galaxy to the entire universe. There are, in fact, anthropic principal characteristics of the universe that suggest that they have been designed with man in mind. For example, we are in a universe that is dominated by three-dimensional space. There is a possibility, in theory, that space could be four-dimensional, or five-dimensional, or six-dimensional. Or it's possible it is actually multidimensional like that, but some of the dimensions are really small and don't make a big difference. We're in a universe that is dominantly three dimensions. Now, why is that important? Well, there's people around the world who like to play with eventualities or possibilities, and they love playing with mathematics. And they like thinking about, well, what would it be like if the universe was four-dimensional or five-dimensional? And these folks, and I'm going to rely on them because I don't know how to play these kind of games, and I'm trusting that they're telling us the truth. But these folks tell us that if you had a fourth-dimensional universe, you would have a problem with things like gravity, things like electromagnetism, that if you had a fourth-dimensional universe, the Earth is spiraling around the sun and has to stay within that Goldilocks zone, which works fine in three dimensions. But if you have a fourth dimension, which is a very large fourth dimension, then the Earth could actually spontaneously fly out of that Goldilocks zone in the fourth dimension, and we'd be in big trouble. We would die. And that is basically not possible to be prevented if the universe is four-dimensional or five-dimensional or six-dimensional. So we're in a situation where if we had more dimensions, we couldn't have stable planetary orbits. The Earth wouldn't be able to stay at the proper distance away from the sun. Similarly, the electrons going around atoms, which allow atoms to be made into molecules, could never stay in proper orbits around the nuclei of atoms. And if that was the case, they could never combine with other atoms to make molecules, and life wouldn't be possible under those circumstances. So it appears as if three dimensions is you can't get anything more than three dimensions, or life wouldn't be possible at all. And if you get down to the one dimension, geometric point, or a line, and you get into two dimensions, a flat plane. So people have speculated about flatland, where everything's flat. There's no third dimension. The problem there is there's only so much complexity you can have in one dimension, and you can have more in two dimensions, but not enough complexity. You couldn't have enough, let's say, molecules, different kinds of atoms, to in fact generate the complexity that's necessary for life. It turns out it's only at the third dimension where you can get enough complexity in components of things to have the complexity necessary for life. So it appears the three-dimensionality of the universe is what is necessary for life. Any other dimensionality would in fact be destructive to life. There's also another issue, which is the plus minus topology of space. And what this means is three-dimensional space that we have is such that you can move back and forth in space. You can move back and forth this way, back and forth up and down, back and forth. All three dimensions of space, you can move any direction in them with no trouble whatsoever. Time, however, you can only move in one direction. You can't move backwards in time. You can't even stay in one place in time. You have to move in one direction through time. So whereas in space, three-dimensional space, we can move any direction we want at any point in time we can only go in one direction. The consequence of this is, again, profound. If you had time where you could go backwards and forwards, again, by those people that figure these things out, that have that kind of time, that can, can do these things, and play with these kind of mathematical equations, it turns out that you wouldn't be able to have stable orbits around planets or stable orbits of electrons around nuclei of atoms. You wouldn't be able to have molecules. Life wouldn't be possible. So you need not just three-dimensional space, but you need to be able to move back and forth in three-dimensional space and move in only one direction, forward, in time, or else you would create a situation which is impossible for life. You also need in this universe to have regular rules on how the universe operates. House rules, if you wish, on how things operate. Consistencies in the nature of things that happen in the universe. If you have inconsistencies, life isn't possible. Life is dependent upon regular laws and rules about how, in fact, the universe works. So it's necessary that the universe have regular rules, which it does. It has what we call natural laws. But not only should it have natural laws, it needs very particular natural laws. For example, it requires something we call gravity, something that will hold planets to the sun, more particularly the Earth to the sun at just the right distance and keep them at that position through time. We need gravity to have the Earth stay in the Goldilocks zone. If we didn't have gravity, life wouldn't be possible. We also need electromagnetic force of the universe because that holds electrons around the atom nuclei, which allows then atoms to come together to produce molecules, which allows life as well. So we need particular natural laws, not just general regularities of the universe. We need specific regularities, like the regularity of gravity, the regularity of electromagnetism. We also need the regularity of the second law of thermodynamics. The second law of thermodynamics uses that unidirectionality of time to cause things to happen in a particular direction, to cause chemical reactions to move in a particular direction. If they didn't move in that direction, reactions wouldn't go in predictable directions. And again, we wouldn't be able to survive. We wouldn't be able to, in fact, move the oxygen from the atmosphere into our blood in a particular direction. That's caused by the second law of thermodynamics. We wouldn't be able to get rid of the waste carbon dioxide in our blood and have it go into our lungs so that we exhale it. We'd accumulate carbon dioxide and it would kill us. We wouldn't be able to take oxygen from the blood and get it into cells. We wouldn't be able to take the food from the blood and get it into cells without the second law of thermodynamics. There's a whole long list of things that happen in a particular way, a particular direction, absolutely essential for life, that is in fact determined by the second law of thermodynamics. So we need at least these three laws, not just any regularities, but these three particular laws and others to have life persist. But in addition to those laws and those particular laws, we even need those particular laws to have the particular strength that they do. In gravity, for example, there is a rather well-known equation that characterizes the force of gravity. The force of gravity between two objects is equal to some number, the gravitational force constant, times the mass of one object times the mass of the other object divided by the distance between the two objects squared. Very interesting chemical formula or mathematical formula. The force is equal to the product of g, the gravitational force, times the masses of the objects divided by the distance between them squared. That particular equation could have been different. It could have been r cubed. Could have been r to the first power. It could have been multiplied by r. Why does it have the particular mathematical form that it does? Turns out from those people that like to play those games and think about other ways that gravity could have been, that other forms of gravity, r cubed, r to the first, do not allow or permit regular magnetic gravitational fields that hold the Earth to the sun. The Earth again would be wandering or in fact flying out of the Goldilocks zone and life wouldn't be possible. And again, in the case of electromagnetism, it's got an equation looking very much like that equation for gravity. The force of electromagnetic attraction between a positive and a negative charge is equal to a constant, the Coulomb's constant, times the charge of one particle times the charge of another particle divided by the distance between the two particles squared. Kind of very similar to the equation for gravity. Again, those that play with these things have considered the possibility, what if r is cubed, or to the first, or not a negative 1, negative 2, but in fact a positive 2. All these other variations would create situations, so they tell us, that would not allow stable electron orbits around atomic nuclei, and thus atoms wouldn't get together regularly with other atoms to produce molecules, and life wouldn't be possible. So not only are there particular rules in the universe that have to be there, but there has to be particular strengths to the forces in the universe, to those regular phenomena of the universe, for life to be possible. In fact, in the case of the electromagnetic force, that K, that kappa, in that equation, the Coulomb force constant times the product of the charges divided by the distance between them squared, that kappa, or K, happens to be a particular size number. If it was a little bit bigger, making electromagnetism a little bit stronger, then atoms would hold on to their electrons with greater strength, and they wouldn't permit another atom to borrow an electron. They wouldn't allow electrons to run between two atoms and hold the atoms together to allow for the building of molecules. And if there weren't any molecules, you wouldn't be able to produce the complexity needed for life. That's if the Coulomb force, the K, the kappa, was a bit stronger, just even 1% stronger, life wouldn't be possible. If kappa was 1% weaker, then the electrons would be held much less loosely, in fact so loosely that they'd just go spin off into space. And atoms, atomic nuclei, wouldn't be able to hold their electrons on at all. And if they didn't, you'd have a bunch of nuclei that are positively charged. They wouldn't want to have anything to do with each other. They would be repelled from each other. Atoms, again, would never come together to produce molecules, and life wouldn't be possible. Wow! Not only is it necessary to have, for example, the electromagnetic force in the universe, but you have to have the force have a particular mathematical form, and you have to have it have a particular strength. Within a range, can't be 1% stronger, 1% weaker. If it's outside that range, life isn't possible. This universe has to be very precisely, finely tuned for life to exist. Otherwise, it wouldn't exist at all. What we've examined so far is we've examined a set of characteristics for the Earth that make it look like it's designed with humans in mind. We've looked at characteristics of the solar system that make it look like the solar system was designed with humans in mind. We've examined characteristics of the galaxy and of the universe that make it look like the universe and its components were designed with humans in mind. All of this suggests that there is a creator who, at the beginning, long before we came into being, with us in mind, provided for our needs so that we could exist in this universe. In the next lesson, we're going to look at characteristics of the world of the very small that indicate that it is designed, again, with humans in mind.